So this is the start of chapter 13 notes, and chapter 13 is going to be focusing on solutions. So a solution is a solute dissolved in a solvent. And there are some terms that we're going to be using. Most of the time we use the term soluble and insoluble. Soluble means something will dissolve. Insoluble means it will not dissolve. You might remember the insoluble term is what we use for if something made a precipitate, if the ions got together and made a precipitate. So two other terms you might hear are miscible and immiscible. Miscible means the same as soluble. Immiscible means the same as insoluble. Okay, so those are going to be some terms that you should know. So in your notes, draw yourself a beaker. Okay, and in this beaker, you're going to have water and you're going to put in a solute. You're going to put into a solute. So this is calcium chloride that I'm going to put in there, calcium chloride. So again, we talked a little bit about this first semester, so this is kind of a review. So I have calcium ions and I have chloride ions. So remember, oxygen end of the water molecule is negative. So you're going to essentially surround the cation, whatever the cation is, by the oxygen end. And then the hydrogen end of the water molecule is going to be pointed towards the anion. In this case, it is chloride. And that's really how you show that something to dilute, something to dissolve. The other thing that we mentioned first semester is, again, proportionality. So since I have two chlorides, I need to show two chlorides in the beaker versus a calcium ion. That's still going to be in place. So we're going to talk more about this actual dissolving process step by step in this lecture. If you go to my list here, when we're talking about making a solution, we mostly talk about, of course, solid going into liquid. So when we're dissolving something into water, that's typically what we think of as a solution, and for general chemistry students, that's usually what you're looking at. But what I have on this list is other things that you could consider to be solutions. So like liquid into solid, again, dental fillings. One that we're going to talk about a little later in the lecture is alcohol into water. So that's liquid into liquid. And we did mention a little of this when we were doing gas laws, gas bubbling in through a liquid. That is also a solution. We have carbonated beverages. So that's really the purpose of that list there, more than for you to kind of memorize or anything like that. So when we are talking about solutions, okay, we're going to be talking about concentration of solutions. So molarity is the one we're going to use most often. And please note, solution always means solute plus solvent, and we will be making a distinction in this particular lecture that we didn't do before. It's a capital M. You could also write it as moles over liters. But this is going to be, again, the big one that we need to focus on compared to the other ones I'm going to teach you in this chapter. This chapter does have a couple topics that kind of show up here and then don't show up again. Then you have something called mass percent. This one you might have already used in biology class. When you talk about a 5% solution, you're just talking about it per mass, because biology people don't use moles. So mass percentage, again, you occasionally see it in your everyday life, so it's not bad to know what it is. But really in chemistry, we use molarity. The other big one that we're going to use in this chapter is something called molality. It's the lowercase m. Now, please recognize that it is moles of solute, which is the same as molarity, but what's on the bottom is very different. This is kilograms of solvent, just the water or whatever you're dissolving into. The lowercase m is the unit, or it's moles over kilograms. Can be used for that. We're going to use molality for one particular calculation called colligative properties, and then it kind of goes away. And then finally, we have something called mole fraction. We talked a little bit about this when we were doing gas laws. So this is, again, capital chi, moles of X over total moles. So sometimes you will see mole fraction as how much of A versus the total. We're going to use this in a couple things in colligative properties, so that's why I'm bringing it up again. And then I gave you a statement. Generally, for dilute solutions, molarity is less than molality. And so that is due to the fact that molarity is liters of solution, while molality is just kilograms of solvent. So that is why you will see that the molarity number is usually a little bit smaller than the molality because of that. All right, so let's try some calculations with this so you can kind of see how it works. So a solution prepared by dissolving 66 grams of urea in 950 grams of water has a density of 1.018 grams per milliliter. Urea does not dissociate, okay? We're going to come back to that concept. What that means is it doesn't break up. So it's really just one particle in there. Express the concentration of urea in the aqueous solution in each of the 4 ways. So the first one is mass percentage. That's very straightforward. How much urea do you have is 66 grams. And then you have 950 grams of the water. So you take 66 plus the 950 grams on the bottom and multiply it by 100. Okay, so you get about a 6.5% as your mass percentage. And again, we're just not going to use it that much, but I do still like to go over it. Find the molarity of the solution. So this is moles per solution. Okay, so moles is easy. Okay, that's just taking the 66 grams and dividing it by its molar mass. So urea, when you add it all up, is about 60.1 grams. So you get 1.098 moles of the urea. That's straightforward. But the tricky part is liters of solution, okay? So realize I gave you density, okay? So anytime you see density, you're gonna have a calculation like this to think about. So I'm taking 66 grams of urea and I'm adding it to 950 grams of the water. So I have a total of 1,016 grams of the solution, okay, all of it. Well, what can I do with that? Well, if I need the liters to do a moles over the solution, I need to use that density, okay? That's going to give me how many milliliters, that many grams of that whole solution is there. And then I convert it to liters because I need that for my molarity calculation. So in this case, it turns out to be 0.998 liters of my solution, So all I got to do is take that number over that number. So take 1.098 moles over 0.998 liters. And I get about 1.1 big M. Okay. All right, what is the mole fraction? So this is looking at urea over urea plus water. So this is going to be 1.098 moles of urea, 1.098 moles. Well, how many moles of water do you have? So you have to do that calculation. Again, we've done this before in terms of finding moles, so that's not a big deal. So it's 52.7 moles. So I write that there. So what you're always going to see with mole fraction with solutions is it's going to be a tiny number, okay? Because you're going to have many more moles of the water than you are of anything else that you're dumping in there. So the mole fraction doesn't make a lot of sense for use of just looking at solutions, but we do use it for another reason. And finally, molality. I've done all of the hard work now. I have my moles of urea. And this one is actually the easier of the two, molality compared to molarity, because I know how much water I have in there. So this turns out to be 1.2 little m. So recognize that the molarity is 1.1 and the molality is 1.2. Like I said, typically molarity is a little bit smaller than molality. All right, so why don't you try this next problem? Write down the formula of sodium carbonate and see if you could do the calculations. I'm going to pause the video and then come back with the answers. All right, so first off, I took the 85 milliliters of the solution and I used the density to find the number of grams. And then the sodium carbonate, I took the fact that it was 14% by weight, so I multiplied it by 0.14 to get 13.6 grams. And again, if you haven't heard me say this a million times, however you get to the answer is going to be fine, as long as I could see how you got there. Molarity is actually pretty easy. Once I have the 13.6, I divide it by the molar mass, which is 106, so I get 0.128 moles. I divide that by the solution, so this calculation was pretty easy compared to the last one we did. 1.51 is the molarity for that. So the tricky one was the molality, because I don't know how much water I have in there, I know how much solution I have. So I was told I have 85 milliliters of the total solution, and I do have the density. Anytime you see density, use it. So that's going to mean how many grams of solution I have total. Well, I know how many grams of the solute I have. I had that from part A, which is 13.6. So then I have 83.8 grams of water for this calculation. I take the moles over the kilograms and I find my molality. Again, with any of these types of problems, if you get this first part wrong and you follow it through for the rest of the problems, you're going to get full